Good. So maybe then we start now. You start.
So,
So yeah, it's a great pleasure having Igor Svynarskyi from Kiev. Igor is actually a young investigator. He's still a master student. He finished his bachelor also in Kiev in Polytechnical University, and now he's doing masters at Kiev Academic University. Today, Igor will tell us about how to predict the superconducting transition temperature in materials using machine learning methods. We look forward to your talk.
so thank you for the introduction. As Oleg said, my name is Ihor, and I am student of Kiev Academic University. And today I'll give you a small talk about predicting critical temperature of superconductors with machine learning methods. So maybe let's start our journey into this. Uh, into this talk. So maybe the first we would like to talk about the motivation. Why do we need to study superconductors? Because superconductors are cool and sometimes extremely cool, like with some uh, literally very low temperatures. And we have some theories about superconductivity, but we could not tell if material is superconducting or not simply by looking at this material. We need to do some measurements. And even if we know that the material is superconducting, it's really hard to tell the actual value of transition temperature because we have different mechanisms and different phenomena, like in high temperature superconductors. So we don't have a theory explaining it very well in much details, and we have a lot of plenty others unconventional superconductors where there is like no established theory. So let me quote some paper uh, like saying that uh, we have multiple classes of materials with similar crystal structures and composition and physical properties, and so we can estimate that superconductivity is driven by the same physical mechanism, but we can't actually predict is material superconducting or not and its critical temperature. So uh, by only theoretical meanings. So we could use something else like machine learning, and it was one of the pri- primary, maybe first really big papers about predicting critical temperatures of superconducting using only their crystal structures, some information about the like formula and some properties chemical. So here we can see the let's try this one. So you can see from this paper, it's they tried to predict the critical temperatures, and in general, it works more or less good, but not exactly the same as as it should be. So, in our work, we are using a database from this paper, and it utilizes, as you can see, superconductor database made by Stanev. It consists only of the chemical formula and the critical temperature of the material. So then we are matching these compounds from this database, and it goes to this uh, workflow from this paper, and then we add some details in our work. So let's maybe dive more in details, slightly details. So basically, we have a formula of our superconductor. Then we match this with some entry from materials project database. It's basically a database consisting of DFT calculations. And after this, we have in our training set, and then we add some features about chemical properties, about atomic environment. So it's some kind of descriptor describing the atomic environments of atoms in unit cell of our compound. And then we have some really basic DFT properties. And then we combine all this data for our superconductors. And this is how authors of this paper created their dataset. And
Oh, sorry, one question. So in the supercon database, there is a chemical formula and critical temperature, right?
yeah,
So based on that,
based on
so given chemical formula, there can be different actual states. I mean,
yeah, different unit cells and so on. Yes.
so what's the procedure on how which ones to choose actually given the data from the materials for the database?
So actually, it's done not by me, but the authors of the paper.
Okay.
So I'm only using it, but they have like some algorithm to match them. So if it's in case if it's in supercon, it's might be non-stoichiometric compound. Then they can like create all these features from entries of some proxy structures in material projects. So like it's combining stoichiometric into non-stoichiometric compound and then just averaging their properties. But in most cases, it doesn't pay much attention actually to their if it's like if you see crystal structure or something else, it's arbitrary choosing. So yes, it's one of the problems of this approach. So limitations because we don't know actually in supercon which one is actually the compound is. Yeah, nothing else. Yes. So it's basically the starting point, but it's a problem because in supercon it's not every time mentioned if it's some kind of specific phase, let's say. So,
So how many materials and how many features do you have?
so we start with 4,000 of superconductors, some number of non-superconductors, but we don't use them. And features, it's like around 9,000 features and start.
But so it's like local descriptor somehow
Yeah.
like tool him for structure. So what was the procedure?
I will talk about it later. So you can. Now it's just outline of how it's working, and I will go into details
But that's the
later.
features for local subdescriptors. It's not not the features for crystal like structure.
No.
So
This disordered hope, it's not like standard soap. It's modification used for the like say average and local environments of
I
the
feel it's
items.
like is it like feature for local descriptors or it's like features for crystal structure after you somehow average like subdescriptors.
For compound,
Okay.
for the whole compound. So it's like assigned to each compound just this long vector of 8,000 vector components. So what we were doing is tried first of all is to reduce this enormous amount of features because it's unrealistic to train something with only this number of samples and this number of features. So we tried to do a PCA, like dimensionality reduction. Then we just clean it slightly because the authors really didn't pay much attention to the features they were working with, and then also do PCA for the other descriptor for like chemical properties, basic chemical properties, and after this procedure, we reduced it from like 9,000 to only 900 features, like 10 times smaller. So with this data set, we could actually try to apply few machine learning models that, let's say, they are primitive. There is no neural networks or deep learning or something much complicated because of, you know, not enough samples. Yes, you basically couldn't train a good neural network on this amount of data. So it's like only k-nearest neighbors, random forest, and gradient boosting. And so it's for this part, it was only like utilizing this data set with some dimensionality reduction and models, but then we also wanted to add something about electronic density of states, because in previous studies it's always omitted, like, but we know for sure that electronic structure, at least in form of the density of states, is important for the deriving superconducting properties. So we tried to add some kind of fingerprint of the DOS for this compound, resulting in doubling basically our number of features and slightly reducing the number of dataset, because not for every sample we could assign some DOS. And yes, and let's maybe dive into details of the dataset. So yes, so it's how it works. They have formula, they have critical temperature, and they have some structure from materials project. Then they are comparing them if like say numbers exactly the same of the atoms, so it's 1, 2, 3, 7. If it's okay, then they assign it as this one structure. If no, they are trying to let's say do some artificial doping on these compounds of these compounds to match these compounds. This is algorithm maybe I will like explain it maybe little bit later, but I don't want to dive into these details. And after this, it's outline of their dataset. So it consists of 4,000 samples. And if we are talking about their class, so it's like around 2,500 of conventional superconductors, assign them as conventional, some number of cuprates, iron-based, heavy fermion, and others. And yes, so let's look into features. So first features from the materials project is basically cell parameters, structure, energy, some information about crystal symmetries and magnetic properties. Then they are also using this MACPI package, let's say. So it's creates some vector descripting basically atomic properties. So it takes only into account, it takes only atoms present in compound. So it's not looking at the structure, but only at the composition, and calculate some statistical, let's say, parameters of these compounds. And then it creates the vector of this length as a feature for each. And if we are looking at the soap, first we will look at the basic soaps as it's shown in this paper. So first of all, we have our, let's say, structure, and we are looking for some crystal site. Then for this site, we are expanding basically atomic density, I would say, expanding atomic density into this smeared Gaussian peak. So instead of this perfect structure, we would have these fields of Gaussian peaks instead of atoms in the environment. Then we expand these fields into harmonic, not harmonic, how do you call it? Spherical harmonics, yes. And some radial basis functions. This radial functions is just Gaussian orbitals. And you do it for a specific site centered at this point, and you can do it for every site in your unit cell. And how do you like obtain these coefficients? It's pretty simple, and you are using basically these coefficients of this expansion as your feature vectors. So the structure would resulting structure of this almost 9,000 components is like this. So we have this big vector, and it consists of the blocks of all unique pairs of atoms. So if you Z1, Z2, you can imagine this as Z1 is, for example, iron, and Z2 oxygen or whatever, and you, for all these possible pairs, you are looking at, if green is ferrum, iron, so you're looking at these pairs. Then for each pair, you expand it into all these possible combinations of Gaussian functions. So you can see it's basically the structure of these coefficients. So and for each of these Gaussian orbitals, you have expansion these coefficients as elements here. And this is how it works for like basic solve for like single atom. But we want to describe with this stuff not atomic environment of a single atom, but some kind of average atomic environments of the atoms in the crystal structure.
Sorry, so once again, okay, so all the pairs, you may construct a matrix of all the pairs with some property, then you actually make out of it a vector and interpret this as a feature, right? And
basically, yes.
And so these coefficients of the expansion, you also take them as features, or
yes. So we take these coefficients as down here somewhere. So it's
okay. And actually, so there's an infinite sum, right? You have to some point you have to terminate it.
Yeah. You have some like.
So how many of them do you take?
In this paper, in their paper, they were taking like 10, probably 10 Gaussian functions and around 9 or 8 spherical harmonics. So this is exactly why it would result in 8,000 components, because.
But do they have an indication why they take this amount of? I mean, why do they take only time the ninth order and the terminate at this point?
Only computational complexity.
Yes, I mean, it's really.
You mean this is how many you can actually calculate?
Actually, yeah.
Yeah. So yes, basically, for like 10 harmonic functions, spherical harmonics, it's more or less automatically computed. And
cut off that depends on the complexity of the structure.
But it should be somehow uniform for very different compounds. Yes, so you have in like, let's say one compound is like heavy fermionic with uranium, and in your data set, and on the other hand, you have something like magnesium boron 2. So you need to account for each possible element in this. So because you have like around 80 elements, and for each pair of these elements, you create in the huge vector. So yes.
So you mean there is actually no any good physically backed reason just how many of them to take?
Yes, basically yes, because I mean it's their interpretation, so no particular reason, but it's only you need to stop somewhere. Yes.
Yeah.
So yes.
Yeah, but that's about of course like angular and radial resolution, which you can capture by this decomposition. But also limitation is the number of species, as you correctly said, they see. It also depends on the number of species in your data set. Let's say that you have like only copper and oxygen. That's like will lead to small.
Yes, but we are trying to account all the periodic tables. So
small, like extract the library of your like sub-descriptors for particular number of specimens, but then add additional element. Want to
They
extend this.
would be
Then
like,
to like rebuild the entire library and
yeah.
plug in new.
So yes, it's basically why they are using almost all possible species here, and it's because it's why for many compounds this vector would consist mostly of zeros. Yes, so it's like 95% of these vectors for most of the compounds is just zeros. So that's why we can then apply dimensionality reduction, and it would somehow work more or less good.
Sorry, one more short question. So if I take one specific compound and calculate this descriptor for this crystal structure, and then I double the unit cell, so I take the same structure just with a copy of the unit cell and recalculate this descriptor, would there be any similarity that I could easily notice between this descriptor or not?
I believe they should be the same because this soap is calculated just only for like one side, yeah, and then they would be for the cell they would be averaged somehow, and if you just double your unit cell and then average it, should be the same thing, but yes.
Yes, I don't know, but maybe the question is whether these functions are invariant with respect to transitions.
Yeah, exactly. These coefficients by itself, they are not invariant. But you see that this P,
this P should be invariant under rotations and some kind of other transformations. So yes, they were trying to do something invariant.
Yeah,
so
but it depends on the composition of this C.
They are not no, but this thing in common is invariant.
Yeah, and it also remarked that, as Ihor correctly said, that that's local descriptor. So it's like descriptor of some local crystal environment. And of course, by calculating, you should like take into account like the images from next cell, supercell images.
Yeah.
So it should be accounted inside during the calculation.
Yeah.
Of this density.
Yes.
Yeah, but
it's
the question if you take one atom and another atom from a neighboring unit cell. So the question is whether these features, whether you can neglect these features or not, or whether they actually add something.
That's controlled by hyperparameter, this cutoff distance, whether to take it or not.
Yeah. If I remember correctly, cutoff distance was like around up to five angstroms or something. So it's like the size of the unit cell. So shall I continue? Yeah. Okay. I just realized there is no smooth transition to the next slide. Sorry. Yeah. So yeah. Okay. So yes, we calculating this descriptors for the particular atomic site, and then for calculating them for each site in unit cell, and then just averaging them. That's how you construct the let's say average description of atomic environments in unit cell. You just take it for every single site and then average around the cell. But this method is only works for like stoichiometric compounds with pretty good numbers of species in the formula. And we know that for superconductors, it's pretty high probability that our formula would have some ugly numbers, non-stoichiometric. And that's why they are using this modification called disordered soap. So it basically looks for our ideal structure. Let's say we have, this formula, and we are searching for similar enough stoichiometric compounds. And then if we can find like two, three, or few, let's say few, these compounds they would calculate the slope of them and again using weighted average construct the descriptor for these structures, but you couldn't find a perfect, like, close enough structure for each present structure. So let's say in this case, it's okay. We can just take this niobium 3 rhenium, I guess, and if we dope it with iridium, we just calculate the slope for this one, and also calculating the slope for this iridium in the place of rhenium. Rhodium. Okay, thanks. Calculating it, and then using these coefficients, we just averaging the contribution of this slope as it would in this one, only in this case. And that's what they are calling artificial doping. So it's basically the procedure to find the similar compounds where we can uniformly replace our atom with some dopant, and then calculate local atomic environment of this dopant, and for all of the structures. And in this case, let's say for this compound, we can't use this one because for Bismuth, we have two non-equivalent Wyckoff positions, and we don't know where this dopant will sit in this type of site or this. So we don't use this one. And yes, in the similar example here, you can see that if we would like to replace it to inject thorium into our compound, it would create a situation where we have for these sites few possible combinations of items. So we don't know which one of these three atoms would be sitting here. So we also couldn't make this doping procedure. And in this case, this doping is not possible because it requires adding some additional site in crystal structure. So it's this method is really messy and hard to implement. But yes, it's only basically it's using the slopes of stoichiometric compounds and then averaging them according to these coefficients, and that's how they create a slope vector for the whole compound. And as I said before, we also try to add some those descriptors because we would like to see if it could make our predictions better. So for each compound, we have let's say materials project parent, even if it's doped structure, but we could assign some similar structure as its parent, and then use the density of electronic states of this structure as basically as those of this one. So it's not really good, but with this disordered slope accounting for this doping, it's worth to try to do this. So what we are doing with the dose, we're basically dividing it on this horizontal, no, on this like bars, yes. So and then we are calculating then we're normalizing it somehow and obtaining this descriptor in similar shape. So it slightly resembles this one, but in more or less uniform way, because for different compounds we have this very different densities. So it's order of magnitude like 10 times or even more might be. So we tried it to do with, let's say, from minus two eV to up to 2 eV, and 0 is Fermi level, with a minimal step over X of 10 millieVs. And yes, it's reduced number of available compounds, but it provided us an ability to add descripting DOS with spin resolved DOS. So but it was only first attempt because we accounted only for the total DOS. So in this case, it's total DOS, not the without resolution of orbitals and species. And the second attempt was to do the same thing, but for calculating this descriptor not for the total DOS, but for those of orbitals of elements. So if we have in our compound ferrum, and then we have the y orbitals, and we for this spin resolved DOS, we are calculating this fingerprint, and we are doing it for the all possible elements and possible orbitals. So it again would result in a vector of this dimensionality, and then we applied PCA and reduce it to more or less adequate numbers.
So basically, you discretize those, and as a feature, you take this one.
The value of the
DOS.
The value based. So it's basically it's good remark. It's just special discretization of those, and yes, and we can do it like for the total dose, but also you can do it for the each specific orbital dose, and that's why it resulted in this enormous number of components. But hopefully the PCA worked fine. Yes.
But the last type would be not rotational invariant, because that depends on the orientation of your orbitals in the structure, and also if you rotate, I guess your orbitals will mix up.
Yep. So it's not invariant, but yes, that's the part we can start it by ourselves. So yes, of course, it's not that brilliant as it might be. And yes, in this case, the number of compounds was this one. So we tried to do it for like smaller region around the Fermi level with slightly smaller step. And because of this smaller step, actually, the size of this one fingerprint for the like single orbital was almost 500 components. Yes, so in total dose, we used bigger step, but also bigger region, but it resulted only in like 200 components. And yes, so basically, our total, let's say, data set would consist of some materials project features, chemical features, this averaged local descriptor, and spin and density of states descriptor. And then we are trying to apply dimensionality reduction on these blocks, not for the whole vector, but only on these blocks, because they are of the same nature, and we can try to do it first on them. So yes, for this one, it allowed us to basically take only half of the features because we could explain the most of the variance by our, let's say, transformation. And in the case of this atomic environment descriptor, it allowed us to reduce it by 10 times, magnitude of 10 times. So then, having this reduced data set, we tried to do a clustering of superconductors just for fun. And here you can see it was done by which one? By HDB scan model. So here you can see the minimal size of the cluster, and here the rate of clustered samples. And you can see, so only for if like we're starting to create clusters consisting only of two compounds. It even in that case, it enabled to clusterize all our samples. So like there is always 20% of the samples unclustered. So clustering is not working on this data set. Yeah, and color is basically different metrics. And it's insightful that cosine metrics basically looking not on the distances but the angles between our vectors in multidimensional spaces best performance, so it would be used later. And so let's try to look at the machine learning part of this.
There is no actually natural clusterization.
Yeah, so yeah, clusterization is failed. So in some clusters, it put like some BISCO or IPCO, let's say YBCO superconductors, some with different dopants. It's could clusterize them in some group, but for some cases it's just some random classes, and for others it's just labeling them as outliers. And
so they in the beginning you showed us classes of superconductors.
Yeah,
there is no way to match this clusterization.
No. So yes, so first yeah, I mean this one.
Yeah.
So yes, it's assigned as like say manually there, and in our clusterization we couldn't achieve it. So yes, clusterization is not working here.
Yeah, I would expect.
But did you play with like hyperparameters of HTTP scan?
Yes, slightly.
So like all these scores for the same.
Yeah, for the best one. I don't remember exactly what was the best one, but for the best one set of hyperparameters, it was not impressive.
Could you one more time recap, like why do you think that there is no cluster there without seeing actually the distribution of points in that space, or like even a projection? Like did you try to visualize the data, like project on the 2D or 3D?
Yeah, tried, but it was messy. But it was like just a bunch.
Large spread or or clusters too small, or like regions not dense. What was
it? Was like one huge dense region, like, and some part of this point painted in one color, part of in different parts. There was like
there is actually some clusterization, but you can't match the cluster label with like label of so to say family of superconductors.
Yeah,
right?
And yes, and also let's say for this one for 10, let's minimal size of cluster 10 and clusterization rate of 60%. It already created like 150 clusters or so. And they were actually, if we try to plot it in 2D, they were like interchanging, not interchanging, but intersect.
So, yeah, but still, you had like these unassigned, unassigned labels. So they like, what was the distribution of these unassigned points? They were like
completely random, I would say, completely random. So yes.
Okay, I can understand why the sign metric, why the angle is more effective in like so to say separation of these points, because you have like very high dimensional space, and of course the distance doesn't really informative there anymore. But angle somehow can capture something, but of course it will be informative to visualize that, and probably can suggest you something.
Yeah, but it was like additional task just to see if we could. It was like a very quick attempt to do it. Yeah, and we didn't dig into it much. Yes, so for the models, let's try look at the hyperparameters optimization. So first one was Kanye's neighbors, which used to optimize number of neighbors, the weights, the way how we account for weights. Is it uniform accounting or with a factor 1 over the distance and metric? And as you can see, cosine metric was better for the hyperparameters optimization. Then for the random forest, we try to optimize the number of estimators and the split criteria, and for the gradient boosting, we try to adjust by optimization learning rate and numbers of estimators. Here you can see the parameter range, and here it's default one is more dataset without DOS, and this one is with total DOS, and this one is with DOS fingerprints resoluted by orbitals. So the results, the most interesting part, the most valuable part. Let's look at the first nearest neighbors, at the models without DOS. So by color, it's highlighting the original superconducting classes. On this x-axis, it's the real critical temperature. On the vertical axis, it's predicted critical temperature. Scale is both log-log, logarithmic scale here and here. And this black line is showing the one-to-one trend. So yes, for the model with total DOS, it looks like this, and for the model with DOS with orbitals, it looks like this. And if we are looking at the metrics, we can see that we have a huge error, like around 7 or even 10 kelvins, so it's not sufficient. But R square for the default model is more or less good, and for the model with the total DOS is also looking good. Total DOS is looking like this, so it's more or less lying on this line. And if we are looking for the random forest models, we can see this for the model trained only on data without DOS, this for the model trained on total DOS, and this for the model trained on orbital DOS, let's say. And yes, we could see slight improvements in arrow and in R square, but yeah.
Do you have statistics on TC distribution for different classes, like whether this matrix, let's say, well, this square root metric is actually like is it comparable? Maybe the
between the classes.
Maybe the variance.
Yeah,
is same order.
It varies. Let's say for the conventional superconductors with low temperature. So you can see that blue dots are basically a line below the 10 kelvins temperature, and for them, root mean square error was around like 5 kelvins, let's say, and for the cuprates shown in red, it was like 7-8 degrees. So yes, but you could also see that their temperature is like on other per magnitude, like 10 times bigger. So for them, having error of like 7 kelvins is more or less okay.
Okay.
And that's why I'm using here log scale, because it's more representative.
So in other words, for high TC, so the method is reasonable, but for low TC, the
yes. And you can see that for random forest there is an interesting anomaly that it actually almost never predicts the TC being lower than like 1.5 kelvins or something, even if we have the materials with lower TC. So it's in the region of low real critical temperatures, it's overestimates the critical temperature, but it's only for random forest. for the, let's say, for gradient boosting, there is no this problem. It's more or less predicting them on the, let's say, on this line. So, but here you can see the Diberide magnum, this small region. It's, yeah, couldn't catch this something. And yes, using the DOS, we achieved more or less, let's say, competitive results. And this plot is looking almost on the line, on this line. Yes, so comparing two best results, random forest and gradient boosting, you could see that, yeah, they're more or less lying on this line, and it's good in predicting coup rates, and but for iron based, it sometimes fails. And
So this line is for training set or
tested.
The whole set?
Testing. Ah, yeah. I forget to mention all these plots are shown for the test set. It was like 20% of the data set. So it's like around how many? 800 samples or something, more or less. Yeah. And conclusions are three, as follows. We could perceive superconductivity somehow. So yes, because as you can see, it tries to place the dots on this horizon on this line. And the second conclusion is accounting of non-stoichiometric compounds is possible if we are using this disordered soap. So it's improvement. Partial PCA is good for the reducing the number of these features because they are quite sparse, having a lot of zeros in this matrix. Clustering was partially successful to say adding those features is improved somehow, slightly improved performance. Then yeah, doing it by resolving on orbital dose is better than doing it for the total dose. So it's, yeah, it seems physically explainable. Yeah, Guinan failed for the data with DOS, it's for sure. But random forest and XGB was good in both cases, in data without DOS and with data with DOS. And what we can do next is to try to construct the, let's say, phase diagrams for the selected materials with different doping. So it's work in progress right now. Then we could try to enlarge the amount of our data by looking at materials project one more time, but it's the most unpleasant one. And maybe we could try to include non-superconductors in our dataset, so it's and then use it for classification, maybe. So it would classify if it's superconducting or not. And the last one thing is to try to screen the whole materials project for the source of new superconductors. So it's basically like predicting critical temperature for each entry of materials project and like choosing the one with the highest critical temperature and maybe asking somebody to check if they are really superconducting. So, and next one is acknowledgements. First, I would like to thank for the Armed Forces of Ukraine for providing me an opportunity to be here at all. Then I would like to thank my supervisor, Volodymyr Bezhuba, for helping me and supervising me. Then Alexander Kurduk for many talks, many fruitful talks about this project, and all the people from my university who supported me, and also IFW Dresden for the invitation, and especially Grit for like supporting me the previous 2 weeks and making all the arrangements. Then all the people from the DESI I met in Hamburg for just these 2 months, and Thank you for your attention, and if you have any questions, do not hesitate to ask them.
Thank you very much, Ihor, for the interesting talk. We had quite some questions during the talk, but maybe there are more.
And there I was compare the different fields with temperature. I noticed that the temperature is higher usually the same field, especially if the machine field. For example, here,
Yeah. This is a mystery. Unknown, because it happens mostly for these random forest models for no reason. Actually, I don't know why. Let's say for the gradient boosting, you can see that it's equally underestimates and overestimates, especially in the region of lower temperature. And for example, in the paper I mentioned in the first one of the first slides, they were predicting only the superconductors with the temperatures above 10 kelvins. So because here in the low temperature region there is a lot of different superconductors with like many families of superconductors with really different structures, and I suppose there is not enough data to the model to learn on. And the second one is these temperatures are like different, very small.
Traditionally, one you choose is almost constant.
Yeah.
But could it be because your cost function is constructed in such a way that it cares more about the materials with high TC? So this actually
I
is
guess
a logarithmic scale and probably doesn't care too much about this region with low TC.
Yeah, but I guess we used, how do you call it, standardization. So we squeezed our data into our critical temperatures in the training. We squeezed them in the region between like -1 Kelvin and +1 Kelvin. So, and it was like more or less Gaussian distribution of these temperatures.
I see. Mm-hmm.
So
my question is, so you have the, let's say, HTSC or cuprates, right? You have data for that, and you also have data for the conventional superconductors.
yeah.
Is there any indication that your predictions for the HTSC get better if you include the information of the conventional superconductors?
They certainly didn't change much. Don't get worse if we include in the conventional superconductors. So it stays on the same level if we are using only conventional. Let's say if we're using only cuprates, and if we're using cuprates plus conventional, the results are on the same level. So there is no indication that it's get better, but for good, it's not getting worse. So it's more or less this model is suitable, let's say, for the whole range of the temperatures to some extent for different classes. So it's probably a better to like can predict each possible class.
No, it's modular, right? You could also have considered them separately, and you could have gotten more or less as good.
Yeah. So, but if but okay, if you are training your data only on conventional superconductor, it would never predict these high temperatures for cuprates.
More questions? Yeah.
I have a question about the deviation from predict the sort of right. So the determine the reason and what's the reason for the deviation from the prediction now. So is it just a sort of so let's suppose as a gamma or something, or this is the sort of just a what's the reason? because for example, if I see the so I'm using different case, so deviation is always, but so temperature case is very slow. So functional wise also is there so deviation so which depend on the so one
To be honest, I'm not sure how to answer this
I
question.
guess conventional superconductors, they are more probed. I mean, the variance in features is much more.
Yeah.
But for cuprates, they are like class itself is smaller. There is less variance, and this is like at least this is what I could explain.
Yeah, I would opt for the same in section.
Could you quantify? Is that quantifiable? Let's say. Actually, you can just measure the variance of features for two of the classes, and then I would expect that you will see that the variance in the first class is much higher.
Yeah, I mean, when we were trying clusterization, most of the group rates fall in one or two classes, while conventional superconductors were falling in 100 classes, and many of them was like not falling into any class, being outliers.
Yes, since the descriptors are mainly based on the crystal structure, of course, for cuprates are relatively simple, similar to each other. So the descriptors are also similar, and noble superconductors are very diverse.
This deviation like error also, like a static errors. So because the sampling is a very, there are many different sampling for the superconductor. For example, normal general superconductor. Conventional superconductivity, but different bases less sampling. So because the material is less.
Materials are similar and the descriptors are similar and the PCs are similar. So I think that's a kind of ideal case where machine learning, of course, picks it. And for conventional superconductors, the structures are very diverse. Can be anything, and the PCs are also quite distributed. Yes.
Yeah. So yeah, basically, group rates mostly has temperatures around between like 50 kelvins and 150 kelvins. So it's like on the same order of magnitude, while conventional has from basically low, actually slightly lower than 1 Kelvin. It's like 0.5 up to 10 kelvins, even more. And in case of the bright magnum, it's 40 kelvins almost. So it's like 2 orders of magnitude distribution. So they are broader distributed and
do we have questions from the online audience from Kiev?
Not much, since we can. The idea was that you have possibility to ask questions. I just probably wanted to ask about orbital dose, not to forget. So actually, I didn't get. Don't remember. Maybe if you explain how do you define it? I mean, for multi-component multi-component materials, how you know which orbitals you should choose.
Here we were using it only for the like wait a minute.
For
So
D metals or what?
no. We were using it for stoichiometric compounds, and it was taken from materials project and basically from DFT calculations. And in DFT calculations, when they are performed, you can get the basically this distribution of electrons on the orbitals on certain orbitals for the certain elements, if I'm not mistaken. So you can get like for the you can get density of electrons for
it's
the
clear. Okay, I thought that it is what you introduced. I think that you introduced this filtering with transition to orbital dose. Okay. It was in
No,
the
no, no. I just took them and switcherized them, discretizing them, basically. So yes, it's not that I introduced the resolution of those bi-orbitals. It's just taken from the DFT and then processed by me.
Okay, thanks. Good talk.
Physically, if you would say for the low TC compounds, the lattice is definitely important. Because it's phonon-driven superconductivity. Somehow that information is kind of lacking from all the everything you considered, right? So even the atomic number probably is not in. Right? So it would be if one would this kind of intuitively one would say that if you want to improve the conventional superconductors, at least some information on phonons or on the lattice vibrations or electron phonon coupling, even that kind of stuff should flow into the model.
Yes, but then if we are doing our model for the whole number of superconductors, we will need to include the information about phonons and vibrations even for the cuprates, and cuprates have big unit cells, and calculating the phonon properties for the big unit cells is quite computationally high.
That you can make it as difficult as you want, but at the moment there is not even information on the atomic weight, right?
Yeah, no, the reason
because it's in the chemical formula.
So yeah, maybe. I have an additional slide. This. Yeah. So features taken from material for this one. So in this MACPI descriptor, we had let's say some statistical information about atomic weights, covalent values, atomic number even. So it's basically it looks at the formula saying we have iron and oxygen, and then like 10 oxygens and 5 iron atoms, and then we are just calculating average atomic weight, taking minimal atomic weight, maximum, and standard deviation of this. So it's accounted in some form. It's accounted for.
Yeah, so this original paper by Stanek, it was published 7 years ago, as far as I remember, right?
Yeah.
And as far as I remember, they also predicted some potential superconductors, some potential new superconductors. Do you know what is going on in this field? Whether machine learning actually help produce something?
As far as I know, Stanek predicted around 14 new superconductors, and none of them was proved to be superconductor. But basically, I didn't see much like attention from community to actually try to synthesize and check. It's maybe one or two were checked, but all of them was.
But maybe you know in any other paper where something was predicted using statistical methods, machine learning, and
No, I've never seen such a paper.
Okay.
Yeah. So yeah, it's reasonable to critique it for the lack of the physical interpretation and implementation.
So there's still room for improvement. So if there are no more questions, let's thank Ihor again.
Thanks for inviting me and fruitful discussions.